Jim Brown. I'm the president of National Test Pilot School. It's my honor to introduce Luke Duffy, Flight Lieutenant, Royal Australian Air Force, C-17 driver before coming to us, and Paul Alvarado, who is a flight test engineer, Naval Academy graduate, so beat Army. Beat Army. And he's in our 3-year graduate assistant program. Their project this year, their final capstone project, was D-Day Doll, the C-53. We gave them a list of requirements to test against. You'll see these. And a lot of this stuff, they're testing this airplane against current military specifications and requirements. And you'll see some maybe not so flattering details. But just understand that this airplane was built in an entirely different era against a whole different set of requirements. So without any further ado, Duff Man, you got the floor.
Thanks for joining us this morning. This is very important for us. The culmination of all of our work for myself over the last 12 months, learning everything in flight tests, putting it together in this evaluation, and Paul as well during his time here, coming together as a team of 2, advised by JB to do this evaluation on an awesome aircraft. Scope of what we'll talk about today, as you can see, we'll have a look at the background and the objectives that we'll put forward to us as a team to assess this aircraft, the missions involved from the user, the evaluators involved in the test program, a description of the aircraft for those who aren't familiar, the instrumentation that was used during testing, what limitations we had imposed on us during the program for the testing, and the schedule we're working towards. We'll then move into the actual test evaluation, focusing on the deficiencies we identified, a quick overview of what was great about the aircraft, and then we'll summarize with our conclusions, recommendations, and an overall conclusion of the aircraft itself for what the user wants for this aircraft. A bit of a background, so put forward to us as a team, so an undisclosed government agency was considering the purchase of a C-53 to provide drug interdiction surveillance and transportation for Spec Ops personnel and cargo. So the C-53 itself is a 1940s era military transport aircraft, and it's developed from the civilian DC-3 for those who aren't familiar. This aircraft is battle tested. It's been used by allies worldwide during World War II for troop transport, glider towing, general cargo, and other missions related to that area. So the objectives we had as a team, we broke down from the user requirements. You can see here, there's 7 general objectives. We were looking at the crew station evaluation, so us as the pilot and crew in the front, how can we do our job? The takeoff and landing performance of the aircraft, as you'll see for the requirements from the mission. Climb and cruise performance of the aircraft for the mission set. The flying qualities, so how the aircraft responded in the open loop sense, and then how we felt the aircraft responded for what we felt through the controls. And then finally looking at navigational capability of the aircraft. To give you an overview of the 2 mission sets, this is the first set. As you see on the right is a pictorial of what is required of the aircraft for the drug interdiction surveillance mission. So we want to provide aerial communication support, and we're looking to work with law enforcement agencies to identify and apprehend any criminals that are looking to transport illicit narcotics. And the profile itself is taking off from a home airfield, climbing to 15,000 MSL. We want to cruise at 150 KTAS. We then want to descend to a loiter area for a 2-hour loiter at approximately 1,000 MSL. Once we've completed those ops, just the reverse of that profile, climbing back up to 15,000 to RTB. We also have a requirement for a 45-minute landing fuel reserve. The second profile was looking at transport for Spec Ops troops and cargo. You'll notice the profile is very similar on the right there. The main difference here is the option either for paradrop operations for a team of approximately 10, or landing on a short strip. And what the user wanted was a 3,000 foot by 50 foot runway. And funnily enough, that's very close to Flaybob Airfield, which we'll talk about. It's a great opportunity to see with this aircraft. Again, the requirement for the 45-minute fuel reserve returning to base. A few additional requirements put forth from this undisclosed user was some performance requirements, namely a time to climb to 15,000 MSL, which is looking at an average climb rate of 1,000 feet per minute. Handling qualities: the aircraft must display level 1 handling qualities during all mission representative tasks. So anything we need to do with the aircraft to complete a mission task, they had to meet our level 1 mil spec requirements. We also had additional requirements that were outlined in our mil specs put forward. Flying qualities: we had a flight path stability requirements. So on finals to land, we had some stability requirements that were outlined in the specific mil standard paragraph, as you can see there. That was a secondary priority. Having a look at the team now. So the team for the evaluation was threefold. We had myself with approximately 2,500 flying hours. Prior to this evaluation, I had 2 hours tail wheel experience and a DHC-1 chipmunk, so it's a big step up for me moving to the Big Bird here. We had Paul Alvarado, FTE on board, 69 hours as FTE experience and 31 hours as test conductor. Then we had Dan, so everyone knows Dan, helping us out with approximately 10,000 hours and then 1,200 plus in DC-3 type aircraft. He was invaluable throughout the whole evaluation, giving us tips and tricks on operating the aircraft to be as efficient as possible and just be really accommodating to get all our testing done. Before we move into the crux of the presentation, we really wanted to add this slide to highlight to all of our colleagues back at NTPS the importance of the history of this aircraft and the aircraft type. So for those who don't know, I'm sure everyone here knows this history, but again, recapping this exact tail number. So it flew in the European Theatre of Operations during World War II, participating in the D-Day invasion, market guard and resupply of Bastogne and the crossing of the Rhine. And so on D-Day itself, this system under test, so this tail number outside, flew 3 missions towing Waco gliders, and we have a lovely pictorial up on the right there, to reinforce the 101st Division paratroopers behind German lines near the Utah Beach. Just moving on to an overview of the aircraft itself, for those who aren't familiar with the specifics of the aircraft. And the reason we go through this is to highlight the aspects of the design that affect our results in our testing and what we're looking at. So a general overview is the crew, 2 pilots, 1 crew chief, general low wing tail wheel with retractable main gear, max takeoff weight 31,000 pounds with a useful load of 14,500 pounds. And the aircraft is capable for day, night, VFR, IFR operations. For the engines, there's 2 options. The ones installed on this aircraft were Wright 1820-56 supercharged Rayleigh engines. So this was the single row 9-cylinder as opposed to the dual row 18-cylinder engine. Same shaft horsepower of 1,200 each. At Hamilton standard 3 blade props attached to each engine, which constant speed with full feathering capability. Of particular note were the flight controls on the aircraft and the design as such. So first of all, canvas covered primary flight controls. Of note, the top picture there, the large aileron surface of the aircraft there, which then feeds into a lot of our findings later for our lateral control, our adverse yaw affected and produced by these large surfaces here. Mechanical, fully reversible flight controls using dual yoke and rudder pedals, and then for trims mechanically controlled for elevator, aileron and rudder. The flaps, split flap design on the inboard part of each wing section, taking approximately half the wingspan either side. That's hydraulically actuated trailing edge split flaps. The point of difference for this aircraft, as many would know, is the navigation systems installed. So, differing from the original build of the aircraft, we have a Garmin G5 dual screen nav system connected to a Garmin nav as well, feeding for IMS-BUI information, as you can see in the top picture, and then the bottom picture, the Bendix King KSN 770 nav moving map display in the center of the instrument panel there, both really useful for SA, and then just that capability in that IFR and night sense as well. Other than that, we have standard original build pressure gauge instruments on the instrument panel. Point to note for this aircraft, and many like it now, the autopilot system had been removed and not available for testing. Just a quick overview of the limitations imposed on us as a team for the program. So in terms of a test program, you normally want as many evaluators as possible to get different opinions and see those different opinions on any handling adverse effects that you find with the aircraft. For this, we just had myself for the opinion there. Moving on to the CG, so the center of gravity position of the aircraft. There was no ballast available. Normally in testing for different aspects, we want to move that CG position forward and aft. We were just limited to the CG position on the day of testing, and we just used the data as such from that point. In terms of statistic relevance, for us in flight tests, we always want to achieve a minimum of 6 data points for each test that we're doing, so we can really validate the information and the data that we are getting. So that was our aim. We had a lot of tests that we wanted to do in this program, and we only had 4 flights to do it, so we had to be really efficient. We wanted to really get those 6 points at least in each test to actually get that relevance. We're looking to conduct some stalls. Dan talked to us beforehand in the planning, advising that an approach to stall needs to be very fraught with caution. We were advised to only test up to the onset of the stall warning, as the characteristics of the aircraft can be quite unpredictable. So we stopped it there. As such, we applied a 10% buffer on that stall warning speed we found on the first test flight. We did all of our testing performance-wise down to a 1.1 stall warning speed. For rudder pedal deflection, due to a rudder lock risk, as advised by Dan, we wanted to avoid that for all of our testing. And rudder lock is when we apply full rudder in one direction, you remove that pressure from your foot and the rudder just stays there, which could be quite dangerous. We limited ourselves to 3/4 deflection. We had a scale attached to the bottom right of the cockpit there to keep us in line with that requirement. Standard limits on the air speeds and the G tolerance for the aircraft, so we didn't break anything and we didn't need to go anywhere near those limits anyway. The last thing was for performance testing for cruise evaluation. We really need to be able to take fuel flow or fuel use during our test points. Unfortunately, the aircraft, the fuel gauges were inoperative. So we still did the testing using an assumption for our power settings and our air speeds appropriately, and then we applied a assumed fuel burn through those phases of flight for our actual analysis of the data. Quick look at the instrumentation. We had a GPS data logger on board, which was really handy for our takeoff and landing performance. It allowed us to see the point at which we touched down and then took off from the runway, giving us really accurate measurements for that. For all the forces and the controls, we had rudder pedals that were assumed, but for the yoke, I had a handheld force gauge. We had a G meter on board, manned by the FT in the back to advise us on our target G during our testing. We had some calibrated measurement sheets attached in the aircraft, and then a tape measure attached to the instrument panel where Dan measured our deflection and our yoke, and then we had the rudder pedal deflection as well that he could read. That's it. To give you an idea of the schedule, those who weren't here during the week, we managed to get everything done in one working week, which was great. We had a bit of crap weather on the Tuesday and earlier in the week, but we managed to get all of our flights done in 2 days with an additional buffer day on the Friday, which was great. Handing over to Paul for the test evaluation intro.
Alright, thanks Luke. So now we're going to get into the meat of the presentation, what we tested, what we learned, what we saw. So this is a general overview of the results. We divided into the crew station evaluation, performance, flying qualities, and handling qualities. Each individual box is a test objective that we tested. If it is green, we found it to be acceptable. If it is orange, it was marginally acceptable. If it was red, it was unacceptable. To kind of give a quick overview of the acceptables, the entry and egress, crew accommodation, cockpit field of view, and the cargo compartment were acceptable for the missions. The takeoff performance, range performance, endurance performance, and the BMCA were acceptable. Flying qualities, the longitudinal static stability, maneuvering stability, lateral directional static stability, short period, fugoid, power mode, Dutch roll, flight stability were acceptable for the mission. And on the handling quality side, the taxiway centerline capture, taxiway centerline tracking, taxi 100-degree turn, precision landing, landing 8-point adjustment, and ILS approach tracking, they're all acceptable. I'm highlighting those now because we're not going to talk about them more in depth for the rest of the presentation. We'll spend most of our time on the marginally acceptables and the unacceptables. So on the crew station evaluation side, the engine controls and actuation and the cockpit noise were marginally acceptable. Performance, stall warning speed, landing performance was marginally acceptable for our mission. Flying qualities, the roll mode was marginally acceptable, and on the handling qualities, the geocollateral pre-play and geocollateral control were marginally acceptable. And then our two unacceptables were the climate performance for the mission, and then directional control and takeoff. The first thing I'll talk about is the engine controls and actuation. So our objective was to evaluate the engine control position and how they move within the cockpit. Does it make sense? The method was during the count evaluation on the apron on Monday morning. We conducted in accordance our own NTPS crew station evaluation handbook. We had two results and analyses stemming from this test. First was the control ordering and grouping, and the next was the mixture level movement. So for those that haven't seen the cockpit and the throttle controls, you have the props, the throttles, the carb heat, and the main throttle quadrant, and then the mixture controls on the far right side. That's depicted here in this picture. Obviously that's non-standard to normal aircraft today. Typically you expect to see throttle, prop controls, mixture, carb heat, it's not really a specified area. And then from the actuation of the mixture controls, the full aft position is the auto rich. Moving forward is auto lean, and the full most forward is auto cutoff, which again is opposite of normal movement for most aircraft. The mission impact is twofold again. Pilot in command may have difficulty reaching the mission controls if the co-pilot is incapacitated during an engine emergency, delaying critical actions and possibly causing additional aircraft damage. Second, a low experienced co-pilot may unintentionally shut down an engine in flight by moving a mixture lever forward to the auto cutoff position when attempting to select auto rich from the auto lean position. There was one specification of compliance we compared this against. It was the Mill Handbook 759 Charlie, specifically paragraph 54125 Bravo. It said a forward movement of any lever control normally should result in an increase in aircraft performance. Clearly, the mixture control lever does not meet that standard. We had a single conclusion and two recommendations. The conclusion is the throttle quadrant arrangement and direction of movement for the mixture levers were marginally acceptable. Recommendation, the throttle quadrant arrangement should be modified in accordance with convention, throttle props, mixture. Recommendation, the mixture lever movement should be modified in accordance with the Mill Handbook 759 Charlie. Full more forward is the auto ridge. Next is the cockpit noise at takeoff. The objective was just to evaluate the cockpit environment during the takeoff. The takeoff power was 44 inches, 25 RPM. And the results analysis were all qualitative, wouldn't have any instrumentation to measure the sound. We weren't really anticipating this. But with takeoff power applied, the radio and ICS calls are very difficult to hear. The co-pilot had to use hand signals to indicate rotation speed, and me trying to test conduct, I didn't realize they were keying the mic to talk to ATC unless I saw Dan physically keying the mic. I just couldn't hear it over the engines. So the mission impact is a lot of the normal cockpit noise with takeoff power applied may reduce the crew's ability to hear incoming radio calls, decreasing situational awareness and crew resource management. There is a advisory circular 2133, cockpit noise and speech interference between crew members. When the noise level in the cockpit exceeds 80 decibels, again, we didn't measure it, the noise will be sufficient magnitude estimate for the normal cockpit communication. In conclusion, the cockpit noise level in the C-53 with takeoff power applied was marginally acceptable. And our recommendation was the cockpit noise level with takeoff power applied should be reduced to a level where clear verbal communication is achievable during the critical flight phases. Next, we'll look at climb performance. The objective of the test was to evaluate the C-53's rate of climb against the customer requirement. Again, sea level of 15,000 feet in the cell in 15 minutes. We used a level acceleration FTT, our flight test technique, in accordance with the NTPS Volume 10, Chapter 831. It's just our handbook for doing these flight tests. The power setting used was 35 inches manifold pressure, 20,000 RPM on the propellers. We did this at 6,000 feet and 10,000 feet pressure altitude, and we experienced light turbulence at 6,000 feet, and you'll see in the data on the next slide. And we did it from airspeeds from 77 knots, which was our 1.1 V-stall warning speed, to VH, which is the max level speed. So on the right-hand side is the graph that we produced from the data. On the blue is the 10,000 foot data. You can see the squares are the individual test points, and the curve produced was a fourth order polynomial. It fits the curve quite nicely. On the red data is 6,000 foot data, very scattered. we had very low confidence in it. We showed it on the graph to show its relation to the 10,000 foot data. In theory, as the higher you climb, your rate of climb decreases. So you expect the rate of climb curves to kind of converge, and also you expect your VY speed to kind of decrease as well. So the curve should decrease and move slightly to the right, and the 10,000 foot data is below and to the left of the 6,000 foot data. So that kind of gave us higher confidence in the 10,000 foot data. For data analysis, when we use the 10,000 foot data, we got a VY speed of 131 knots true and a rate of climb of 526 feet per minute. To compare against the customer requirement, which is assumed 1,000 feet per minute from 0 to 15,000 feet in the cell. So the climb rate of the C-53 will increase the fuel consumption by approximately 70 gallons using Dan's estimations during the climb to altitude, reducing the mission fuel efficiency and the fuel margin for additional tasking. For specification compliance, just the customer requirement, the maximum observed rate of climb of 526 feet per minute failed to meet the customer requirement of 1,000 feet per minute by 474 feet per minute, which is a 47.5% failure. In conclusion, the slow climb rate of the C-53 did not meet the customer requirement and was unacceptable. We recommend the climb rate of the C-53 must be improved to meet the customer requirement. Next, we'll look at the landing performance. The objective of the test was to evaluate the ground roll for the customer requirement. The configuration was gear down, flaps full. The landing technique is as listed above. It was on a 2-degree visual approach path using VREP of 85 knots. Landing with an aim point of the aim point markers, the 1,000-foot markers, the captain's bars, however you want to call them. The evaluating pilot initiated a flare at approximately 15 feet using a low altitude to get a 2-point landing, light braking until the tail was lowered at approximately 50 knots, and then moderate braking to come to a full stop in accordance with our limitation. So again, on the right is a graph depicting all of our data. The individual columns are the 5 test points that our evaluating pilot did. The red line is the customer requirement, 3,000 feet. The green line is our 95% confidence interval. If you were to do this 100 times, 95% of the time, the pilot would stop within 3,275 feet, which does not meet our customer requirement. All the data was normalized to a mission weight, the spec ops mission weight of 25,000 pounds, standard day sea level. And then, again, as Duff mentioned earlier, we got to go to Flayball Airport. Dan was very familiar with our landing technique. We asked him to do a landing using maximum braking, since he was allowed to do that as the owner-operator of the aircraft. Using his data, normalizing it, he did a stop in 2,448 feet. So, using maximum braking. The mission impact is a pilot conducting a short field landing may exceed the runway available if less than heavy braking is used, leading to aircraft damage and injury to crew. Customer requirement was a specification to operate on a 3,000-foot runway at mission weight. Using moderate braking, 3 landing test points did not meet the customer requirement, and their 95% confidence interval also does not meet it. However, the Colorado Air Force pilot did demonstrate compliance by using maximum braking. In conclusion, the ground roll landing distance using moderate braking for the short field operation was marginally acceptable. Recommended caution should be added to the C-53 operations manual. Surprising this isn't in here, but that states that for short field landing operations, touchdown must occur within 500 feet of the landing threshold, and heavy braking must be used to ensure adequate stop performance. And I'll pass it back to Duffy.
Moving on to looking at the stall warning and stall warning system of the aircraft. So the objective was to determine our stall warning speed of the aircraft. We did this pretty much straight away on the first flight, so it anchored our lowest speed for all of our testing at 1.1 VSW. So per the safety pilot guidance, Dan's guidance, we were limited to the first onset of the stall warning of the aircraft. So we went through and conducted our approach to stall as per our normal flight test technique at NTPS. And so we're looking at a 1 knot per second deceleration rate from our setup speed. And then every 5 knots we paused and conducted a controllability check in all 3 axes to make sure the aircraft was controllable and no unsafe characteristics at those speeds. We conducted this evaluation of both cruise and landing configuration. We looked to set up the test point approximately 9,000 feet just to have a nice safety buffer for ourselves. And then the starting speeds were 190 knots respectively. What we saw, so the aircraft was controllable all the way out. It was quite nice handling all the way through to that stall warning speed. The points of note though was the aircraft didn't have an artificial stall warning system installed at all. So all the crew relied on was the feeling of the aircraft talking to you close to that stall speed. And at the point where the stall warning onset came on, Dan talking to us saying, "You feel that? That's the stall warning." I was quite surprised because there was a very subtle indication of light buffer through the controls and a bit of aft force lightening in that yoke right at that stall warning speed. At that point, we dwelled and stayed at that speed just to really feel what it felt like. Dan indicated to us that we were approximately 2 knots above the actual stall speed for the aircraft. This is highlighting a point here. Using what we saw, we recorded a stall warning speed in the two configurations of 70 knots and 62 knots. And then looking at the flight manual, the actual listed stall speed, which would be at max weight, is 68 and 62 knots respectively. So the margin there isn't very big or non-existent at all. And then the subtle warning for the pilot, you really need to be paying attention for that stall warning. So what does this mean to us moving forward employing this aircraft? So something that we might look at is that without adequate stall warning system, typical operational pilot conducting the mission set for the night loiter operations may experience intermittent buffeting through the controls close to stall speed, distracting them from the primary mission task. So they get distracted by that feeling for the aircraft and they get distracted from their primary task of looking for someone on the ground, having to go back to controlling the aircraft, get the speed under control, and then back into the task again. In terms of spec compliance, there's a twofold here. There's a civilian requirement and a MIL standard requirement as well. So we've got the 14 CFR 25.207 and then the MIL Foxtrot 8785 Charlie, particularly paragraph 34211. You can see the two excerpts here. So the first one's the civilian standard, the second one is the MIL standard, and they're pretty clear here. So for the civilian, the stall warning with sufficient margin to prevent inadvertent stalling with the flaps and landing gear in any normal position must be clear and distinctive to the pilot in straight and turning flight. From the MIL, the stall approach shall be accompanied by an easily perceptible warning consisting of shaking of the cockpit controls, buffeting or shaking of the airplane, or a combination of both. So it's pretty clear there, the requirements set forward in the current specs. Taking all this into account, the stall warning characteristics of the C-53, adequate stall prevention was marginally acceptable. We recommend the stall warning system should be installed in an aircraft and comply with both the civilian and the military standards as outlined there. We also conducted a qualitative evaluation looking at the takeoff handling characteristics of the aircraft. A big point of note was the directional control during the takeoff roll, especially with the technique we were using. So again, rehashing for the takeoff technique, we kept it repeatable using the same technique for all of our takeoffs so that we made sure that we didn't obtain any of the distance data, and we also wanted to be able to compare all our takeoffs together. What we did is we lined the aircraft up with the aircraft on the center line, main gear, on the departure end of the threshold markings, the piano keys. Static takeoff was used, so using the takeoff power 44 inches, 2500 RPM applied on the brakes with the control yoke full aft there. And then from brakes release within 3 seconds, control yoke moved forward to lift the tail, forward pressure applied up until rotation speed to keep the aircraft on the runway. And then for direction control, maintaining the center line, only rudder inputs were used, only rudder pedal inputs were used, there was no differential braking used at all. We had some task requirements. So for center line, we wanted to simulate we're on that 50-foot runway. So using a desired adequate performance had us at the edge of that 50-foot simulated runway. For the pitch capture on rotation, we wanted to rotate the aircraft and capture a target 7 nose up within 2 seconds in that rotation speed. We have the requirements of the within 1 degree of our target, no overshoots, or adequate within 3 degrees with 1 overshoot. So what we saw during most, if not all, of the takeoffs, so the pitch capture task, the aircraft behaves really nicely in the longitudinal axis. Pitching up to capture that 7 nose up was quite easy for all of the tasks conducted. However, the centerline maintenance was quite challenging. We have a rating scale system. Normally 1, 2, 3 is quite easy to complete a task, and then moving to the 4, 5, 6 is where there's moderate pilot compensation required to get the task done, essentially. So the centerline maintenance ended up with a rating scale of 4, and then accompanying this with the comments of the difficulties involved in modulating the rudder pedal inputs throughout the takeoff roll to maintain that centerline tracking. So generally what was used prior to brake release, the pilot, myself, had to compensate already using a quarter rudder pedal, and then after brake release this increased to approximately half right rudder pedal, leading that power pull of the aircraft to the left as the engines wanted to pull the aircraft left. This slowly reduced to neutral, approaching 60 knots on the takeoff run, and then small amplitude, high frequency inputs were required to keep the aircraft straight and on the center line up until that rotation speed. Of note, during the second takeoff, I actually did a lateral oscillation. I did not lead with the quarter rudder, and I found myself at the quarter deflection left and right on the runway during the takeoff roll, which was continued to rotation, but just showing how easy it is to fall into that trap of deviating left and right. So a pilot without recent takeoff currency while conducting a takeoff on a 50-foot wide runway may exceed the lateral confines of the runway during the takeoff roll, causing damage to the aircraft or injury to crew. So the spec compliance is that the user wanted us to meet a level 1 handling qualities for all our mission representative tasks. The rating of a HQR4 bumps us down to a level 2 there. So level 1 handling qualities is generally a 1, 2, 3 rating scale, and because of this PIO and the moderate compensation I needed to keep the aircraft straight on center line, it bumps us down to a 2. So in conclusion, the moderate pilot compensation required for directional control during the takeoff roll will not meet the customer requirement and was unacceptable. The aircraft must be modified so that any qualified C-53 pilot can easily maintain runway centerline during the takeoff roll. Moving into now some flying handling qualities, looking at the lateral axis for our control. We're starting with the roll mode, so particularly looking at the roll performance of the aircraft and how that relates to us controlling the aircraft. So we have a test technique that we do, which is setting the aircraft up in a 30-degree angle of bank turn, and then we command a roll towards the opposite 30-degree angle of bank, and we time how long it takes from 30 to 0 to 30, and then we apply this timing to some requirements outlined in the MIL standard. We also have an approximation of what's called the roll mode time constant. This is how quick the aircraft reaches 63% of the steady state roll rate. And so because we don't have any instrumentation installed, we have to approximate this. How we did this is starting in a 45-degree turn. We got the aircraft in a steady state roll. Coming through wings level, I called hack, neutralizing the controls, and then calling hack again when the aircraft stops moving. We then divide this by 3, and that gives us an approximation of how the aircraft, how fast it gets to its steady state roll rate. As you can see here, this is the time to roll in the table displayed on the top. The rightmost box is what's applicable for our MIL standard. That's a 45-degree angle of bank change. It's actually quite slow, and this was the first thing we noticed as a crew, is the roll rate of the aircraft with the combination of the large surface, the long control lines, the big control yoke, and the free plate, all getting involved there to slow down that roll rate with that giant wing and the inertia damping out there. So because of this, there was some moderate compensation required from the pilot to actually get the desired roll rates, and this required me to really drive the control deflection further than I thought initially I needed to get the aircraft to the roll rate I wanted to conduct a normal turn. So relating this then to the mission impact of if you're in that loiter operation and reversing the aircraft over to get your eyes onto something on the ground, you really need to compensate by driving that control further than you need to get to that roll rate. The roll mode time constant again, so it's not only the roll rate at steady state, but getting to that steady state was quite slow. So that 63% was about 1.2 seconds. So getting close to that 3 seconds now to actually get to that steady state roll rate. Slow roll rates and long roll mode time constant will require compensation to conduct mission representative tasks, which will elevate baseline workload of loiter operations, possibly reducing pilot capacity for additional mission-related tasks. In terms of spec compliance, on the right is a table, which is an excerpt from the MIL standard requirement. So to be clear, this is our class of aircraft here. Handling quality levels, we have 1, 2, and 3. The customer wants a level 1. This is the time required to move through a 45-degree angle of bank change. So for us, we recorded 5.4 seconds, which actually falls outside the bottom of the level 3 requirements there. So it's quite difficult to achieve these requirements in the MIL standard. The roll rate and roll mode time constant for mission representative tasks, turning tasks was marginally acceptable. So we recommend the aircraft should be modified to meet the level 1 time to roll requirements as detailed in the MIL standard, particularly that table I showed on the previous slide. Staying in the same space of lateral control, we noted a deficiency which was looking at the free play in the yoke itself laterally. So we wanted to evaluate the flight controls free play in all axes. Everything was adequate barring this lateral axis. And so we were looking at this both on the ground, and we also looked at this during our flight testing, during the roll performance testing, and then just during general handling qualities of the aircraft flying around, simulating flying the mission tasks. So what we saw, it was approximately 20 degrees of free play, and just to really outline what that is, it's movement of the controls, which then had no movement of the flight controls at all. So it was just that slack in the controls where nothing was happening. Each time you wanted to input a control in the ailerons, you have to move through this area and then command a roll. This point contributed to the large control deflections required to initiate the turns, and then also the roll rate, and then also anticipating the roll commands. We talk about control gains during tasks. So high gains is where you're conducting a task where it's quite involved for the pilot to be very accurate for what you're trying to fly, and then the control inputs are not only large but they're also quite fast. So high gains is something we use as a term in terms of quantifying and explaining what it is that we're doing and what we're feeling during a task. This free play definitely contributed to the high gains required for landing tasks and any precision lateral tasks we needed to do. So you'll see in this video flying the approach here at the airfield with down on the right. If you take note of the right yoke, you'll see my movements. Outside, there's not much roll actually happening. It's very small inputs that the aircraft is experiencing. However, the controls do move quite a lot. To me as a pilot, this feels like I'm really over-controlling the aircraft. So artificially, it drives up what I think the perceived workload is for the task, and it takes away a little bit of that mental capacity for anything extra that might be happening outside the aircraft. Coming into land, especially on the ground too, for that lateral control, I end up using large control deflections with 2 hands, again, taking away that mental capacity, where otherwise it might be a bit easier had that free play not being there. Large free play lateral controls could elevate the baseline workload during normal mission representative tasks, which may reduce the pilot's capacity for additional tasks. We didn't have a specification compliance for the free play. However, our conclusion is the C-53 lateral control free play for mission representative tasks was marginally acceptable. The aircraft should be modified so that there is no pilot perceived lateral free play in the control system. Another deficiency looking in this same lateral control sense was the actual control deflection itself. So we now have the pilot compensation of requiring us to drive further to get our roll rate we want. We have the free play we have to move through before we even command the roll, and then this ends up with a large overall control deflection required for our normal tasks. So what we looked at was assessing this control required for all of our tasks for our flying. We assess this again through the roll performance and then qualitatively during pattern work to land and also our loiter turning mission tasks. As you can see on the right there, this is our deflection recorded. So on the right is full deflection, that's 180 degrees. That's actually quite uncomfortable when you're sitting in the seat. Even passing the controls through your hands, it's time consuming and it gets a bit awkward at times. And then on the left is 2/3 deflection. So that and about 90 was what I was using to initiate rolls at the rates that I wanted, especially turning up to that base turn point for the capacity to land. We looked at turns at 30, 45 and 60 angle of bank to see what the effect of this control was. So accommodating this control as well was approximately 40 pounds of lateral force there. So you can imagine that 40 pounds in one hand, if you're manipulating props and engines on that base turn to land, it gets a little bit fatiguing and drives up that workload for the pilot a bit more. Of note, that 40 pounds in the mill standard was acceptable, however, it was in the high end of the acceptable range. So the large lateral control deflections and forces required to initiate turns may elevate the baseline workload of loader operations, potentially overwhelming the typical operational pilot with additional mission-related tasks and external pressures. In terms of the spec compliance, the mill standard looks at the deflections for representative roll rates. So for airplanes with wheel controllers, the wheel throw necessary to meet roll performance requirements shall not exceed 60 degrees in either directions. So we're using approximately 100 degrees to make our normal turn, so a little bit elevated on that 60 requirement. The conclusion from us is the lateral control deflection required to achieve mission representative roll rates is marginally acceptable. The aircraft should be modified so that a pilot can easily achieve loader mission representative roll rates using 60 degrees of lateral deflection in accordance with the mill standard of the paragraph 3345 previously quoted. Over to Paul to talk about the mission profiles and conclusions.
Yeah, so again, when Duff introduced the two missions, there's a profile associated with each one. So this is the drug interdiction surveillance mission. We wanted to find the fuel flow for each portion of the mission is verify that the airplane had enough capacity to do so. Ideally, we would have reported fuel flows or fuel quantities to collect reduce actual data, find an actual best V range speed, best endurance speed, and the associated fuel flows. But instead, we used approximations from Dan. He said about 200 gallons per hour on climb, 100 gallons per hour in cruise, and 70 gallons per hour on border. So using those numbers, we plugged it into our profile. So on the climb from sea level to 50,000 feet, we used 84 gallons. On the cruise out to our descent point is 72 gallons. During the near auto descent, it's 23 gallons of used. To our loader is 140 gallons, and then coming back up from 1,000 to 15,000 feet is 79 gallons. Coming back to the initial airfield, 68 gallons before your descent to land is used 25 gallons, and then the 45-minute reserve was 53 gallons. Altogether, that was 544 gallons approximately. We're comfortable with this number because the aircraft carries over 800 gallons of fuel. So even with some fudge factor fuel using estimations, that's well within the capacity of the DC, or the C-53, excuse me. And then looking at the spec ops transportation mission, again, very similar profile, except instead of the 2-hour loader, you come down for a single landing and takeoff, estimated at 15 gallons used for that. Without repeating all the same numbers, the total fuel flow used is, or fuel used rather, is 430 gallons. Again, that's almost half a tank approximately, so well within the capacity of the C-53 to fly this mission. Now we're going to go to our conclusions and recommendations for our test. This is a summary of our conclusions. We had two unacceptables, the climb performance and directional control and takeoff. Again, those are mostly unacceptable because they failed the customer requirement, not because they were actually truly unacceptable. Marginally acceptable was the engine controls and actuation, cockpit noise at takeoff, the stall warning speed, landing performance, roll mode, yoke lateral, free play, and yoke lateral control. However, we had an overwhelming number of acceptables. Over 7% of our test objectives were acceptable, so that drove into our final conclusion for the aircraft, which was we found the aircraft marginally acceptable. The aircraft was suitable for the drug interdiction, surveillance, and special operations transport missions. The failed customer requirements and identified shortcomings did not preclude the C-53 from completing the mission representative tasks, and the unacceptable deficiencies must be fixed to meet the customer requirements. This is a list of all the recommendations we went through the presentation today in order from the highest priority to the lowest priority. There's 10 of them in total.
Just us as a team, what we learned through this experience, it was great for us operating in a really congested airspace, which was the LA Basin. We didn't anticipate how difficult it would be to find some nice airspace to do our testing. The first flight, we just got pushed around by ATC, and our test points got continually cut off halfway through. We had to reevaluate and then move to different areas to get anything done. So for our second flight, we actually had Dan coordinate with the local controllers to get us an area we could use, which worked a lot better. And this forced us then to be more efficient in our testing. The first flight we wasted a bit of time. We had lots of test points to get done, so we really started cramming them in where we could. So using the climbs, descents, and any of that spare time between our positioning and our test points, we threw more test points in that we missed in the first flight. It was really good for us to learn the experience of operating in congested airspace, because the whole year we've been up near Mojave where we have our special little box that we operate in. You don't really have to think about that stuff at all. So good point for us to learn how to play with others. And then the last point for us is the test item itself, so the aircraft. So we had all these flight manuals sent to us for our test planning. We didn't actually get our hands on the aircraft till we got here, and our test plan was written with all of our testing points involved. We didn't know things like the differences from the AFM, the differences of the cockpit layout, the fuel gauges being an op. So it's good for us to have to be flexible on the spot, and we still got all our testing done with the assumptions that we outlined. But again, it highlights how much we as a team really need to know what it is we're using for the test moving further forward. So again, really good learning outcome for us. Yeah. That concludes our presentation. We really appreciate everyone coming today and listening to us, and we welcome any questions you have for the program or for us or anything about the aircraft. We have some backup slides with extra stuff if you want to look at anything else. Thank you very much.
Very good. Yes, dudes, hit them hard.
Conducting those mill steps, when were they written?
Oh yeah.
87, 85 Charlie is early 70s vintage, something like that. It has actually been replaced with 1787, but we at NTPS use 87, 85 Charlie because it presents the numbers that we're testing against. The other one's more, what do you call it, prescriptive rather than descriptive. I don't know, how about Air Force TPS? Do y'all still use 87, 85? Use 1797? We just choose that. It gives us numbers to test against.
No DC-3 that I ever flown has the throttles and props the way they should be, I guess. Because if I fly with a B-25 guy and say, okay, hold the throttles back, they'll automatically reach the props because it's ingrained in their mechanical.
That's what we're saying about the mixture too, right? So normally mixtures move forward for increasing performance, and how easy it would be for a junior guy stressed if you're operating auto lean in the cruise, you want to go, all right, call for full rich, and just push it forward and kill the engines.
So I think the reason why they put them up by the co-pilot's knee is for that reason. So if it's not right there on the column, so that they at least have to think about it for a second. I have to think about it for a second.
The middle spec, I actually found the report that was done, and it was B-17, B-24, B-25, DC-3, and it was, none of them were the same, and then the primary recommendation out of the report said, hey, we got to come up with a standard, let's just pick something, but come up with a standard, and that's where the order has come from, and that's 1947, I think.
Checklist running standardized will be 17 or prototype is 17, which is 10 years before, 5 years before.
Does the fruit play that you found in the roll, is that, and I should know this, but is that discussed in the flight manual at all? Or anything that you saw?
So,
As a warning to pilots?
Bob Harper, did he think? Bob Harper did a heli-qualities report on this aircraft in the 50s, talked about the exact same thing, and they actually had the instrumentation on the control lines and all that stuff. They could measure the stretch and whatnot. So they talked about things about, it was pretty common along the fleet to just have this stretch over time without any rigging adjustments, generate massive amounts of free play. Also talked about too with airloads on the massive control surfaces that past about halfway, you won't really get much more deflection of the controls because the control control cables would stretch so much under that air load. So twofold problem there. So I don't actually know if you're getting much more deflection. You might only get 40 degrees of actual useful deflection there.
Was it in the flight manual?
I didn't see anything in the flight manual at all.
Like a warning to it.
Right. You know, the 1940s flight manual and what you see today are two different animals.
Well, reading the flight manual was interesting too. A lot of it was just someone chatting to you about how to do something, right? And the short field landing section was nothing. It was something like, consider using full flap if you want. Probably do a 3-point landing, and that's it, right? That's why we had that note to chuck in the operations manual. It says nothing about landing technique, braking technique, aim point, nothing about that. So
Yeah, we have a real C-53 flight manual from the war, and it's only like half an inch thick.
yeah, the one we got was 93 pages. So yeah.
And even the manual that the FAA said is our official manual for this airplane is useless. They took data from flight safety from 1951, if I remember correctly, and they just slapped it all together and said, here's your manual.
He also found on short field, if you put a palm tree on short flight.
Yeah, that's good.
There's an award for that. Somebody's gotten it
It's
in this room. I don't know
simply
who.
trimming deck. That's all it was.
Gopher came by his name, honestly, right?
Dan's landing, was that compensated for aim point and airspeed and all that stuff?
Yep, they'll standardize the same way as the landings at.
So that was a braking difference. Let's give you
Yeah, it's
that.
just purely braking difference.
And a video
They may be
too.
technique, experience.
He's not doing 78 knots in the brick one, I assume.
He touched down about 300 foot in from the threshold. It was pretty tight, but again, that's why the requirement to land within the first 500 feet, which is very achievable, and then using maximum braking, hits that requirement for 3,000 feet. It's still tight. Again, this would go through like risk assessments, right? It's not a guarantee. C-17s too, we operate austere strips with cargo loads where if you land, you can't take off, and that's the risk. So yeah, very interesting.
Now, anything about angle attack? I don't know if you had instrumentation for that kind of stuff, if that even comes into play.
Yeah,
We had no instrumentation for that. That'd be great to have though.
After looking at the V-stall study you did, any thoughts off the top of your head of the approach VREF speed? Is that probably in the ballpark of what versus what you found for actual?
the VREF had a good buffer there, and in terms of like VREF development and whatnot. Again, if we could load this thing up to max weight and do proper stall testing, right, with a proper CG position, then we could actually look at that buffer and see its appropriate nature, but it's just the limitations here. It would have been great to get a fully instrumented aircraft with ballast to really see where these limits were, right, and actually see the stall characteristics of the aircraft as well. It's interesting. Dan talks about his experience with stall characteristics aren't very friendly, and then this report from Harper in 1950 installed it many times, like 25 times. So it was very consistent stall characteristics. So it must be the weight CG position they had for that stall testing. So maybe that affects it a lot too. So.
But you got down to like, did you get down to 68 knots?
Yeah.
Something like that on that? Before you felt?
And when I say I felt something, it was kind of like, hey, that's the stall warning. I go, okay, that's the stall warning. So very, very light buffeting through the yoke, and that a bit of a tinny noise through the airframe, and then that shallowing of the stick force gradient, the yoke force gradient.
You know, when you say we don't have a stall warning system, I have to disagree. The two guys on
Yeah,
these two guys.
Yeah, when we're doing the test, Mike's leaning over and be like, what are you doing?
our stall warning system. So overall, how do you like finding?
Great. What I will say, this is a very objective evaluation, right? The acceptable, unacceptable, marginally acceptable. The overall gut feeling is you can do the job with the aircraft, right? As a pilot, naturally we compensate for things, and there's a bit of that ego involved, but it is a great aircraft. You can see it's well built, and it's very good for a lot of different jobs, which was proven during that era, right? It was used for everything. So we talked about its roles, probably had 30 different roles that it was used for during that time, and then since as well. And you see what it's used for in Antarctica, up in Canada for cargo transport. It's a pretty resilient aircraft, and it's pretty awesome to be able to fly a piece of history, especially this aircraft that flew in World War II.
Yeah, because it's fun. I don't know if I told you, a friend of mine from the Navy was a test pilot, Navy test pilot. His funnel exam, whatever you want to call it, was to take a DC-3 to Australia.
Oh, nice.
And his thing was to demonstrate going out into the desert, being able to land in the, wherever, for picking up emergencies, medical things, or even delivering cargo food or whatever.
Yeah, well, great aircraft for it.
I want to say thank you to the commemorative Air Force team. The hospitality was great. We got to celebrate Thanksgiving with everyone. Just been a wonderful experience. These guys got a lot out of flying the airplane, so thank you so much. We really appreciate it, and I hope this is a continuing relationship. And you guys are just a wonderful gang of folks to hang out. And the stall warning crowd over here kept everybody honest.
It's a highly efficient stall warning system, I'll let you know.
Yeah. Yeah. Thank you so much. Appreciate it.